Yan Tao, where is our first presenter? It's you. Yeah. Do you want to? Your slides are also. Do you have anything like that? Any slides or anything? Or just like this?
Just like this, yeah.
Yeah? Okay.
Yeah. Thank you.
So, welcome to the distributed system session. Just after lunch on the last day of the conference, stay awake. So just trying to be on time here while people are still walking in. The first paper in the session is low overhead distributed application observation with DeepTrace. The presenter is Yan Tao Yen. He's a PhD student at Tsinghua University under the supervision of Han Zhuang. And his research focuses on monitoring and fault diagnosis on microservices.
Thank you for the introduction. Hello, everyone. I'm Yan Tao, a PhD candidate at the Tsinghua University. It's a great honor to present our work here. I will be talking about DeepTrace. It's a novel method that enables accurate distributed tracing for microservices without application code modifications. First, let's briefly review the evolution of software architecture. Traditional systems often use a monolithic architecture. In such systems, modules are communicated through direct function calls. Today, the industry has widely adopted a microservice architecture. In microservice, independent components interact through network calls. While this is beneficial for the software, it introduces significant challenges for microservice troubleshooting. Now, picture a microservice system as shown in this slide. It handles a large number of concurrent requests. Among them, the execution flow of request 1 is shown here. To successfully return a response, a single request often requires coordination among dozens or even hundreds of components. These components must interact and communicate with each other throughout the process. Furthermore, different requests can trigger entirely different execution paths. For example, for the request 2, a different path is activated involving a different set of components. This high flexibility and distributed nature introduces challenges for microservice debugging. For instance, if the request 2 implements a front-end timeout without knowing the end-to-end execution flow, the operators can't determine which components the request passed through or where performance degradation occurred. Therefore, they are forced to blindly inspect a large number of components. In that, they may still fail to accurately identify the faulty backend component. This is precisely the significance of end-to-end request tracing. Next, let me briefly introduce the concept of tracing. We refer to the complete life cycle of a request and its corresponding response as a span. Every span starts when the request arrives and ends when the response is not. In this example, R1 and its response R6 together form span 1. R2 and R3 form span 2. Span 2 is the child span of span 1. The goal of end-to-end tracing is to piece together these spans to reconstruct a coherent end-to-end execution path. Once we have the complete trace of a request, we can quickly answer many important questions. For example, which component contributes most end-to-end latency of the request? Which specific request caused a thread data lock in component A, or is the A/B test running as implicit? However, in deploying a tracing framework in the microservice is not an easy task. Existing tracing frameworks can be categorized into two types, based on whether they require modifications to the application code: intrusive and non-intrusive. Common intrusive frameworks like Jaeger and OpenTelemetry ensure tracing accuracy through the context propagation. Specifically, when a request arrives at the front end, a central controller assigns it a unique trace ID. This ID is then copied and propagated to all subsequent backend requests. Therefore, spans with the same trace ID can be put together to reconstruct the trace. But modifying the application code of every component introduces a series of problems. First, modifying the code of dozens to thousands or hundreds of components is time-consuming. Furthermore, operators need to use different SDKs for components written in different languages. This requires repeated development and maintenance efforts. Additionally, they are unable to cover closed source or third-party components that can't be modified. By comparison, non-intrusive tracing offers significant advantages. Developers don't need to write application code to integrate tracing frameworks, saving a massive amount of development effort. This makes it convenient to use, and it can cover any component and be quickly ported to various microservice applications. But non-intrusive tracing faces challenges in achieving high tracing accuracy. When a component handles multiple incoming requests concurrently, each incoming request may trigger its own set of outgoing requests. From a non-intrusive view, it is inherently difficult to directly determine which outgoing request was triggered by which specific incoming request. This is a core problem that our work aims to solve. We use coroutine-based concurrent request handling to solve this issue. In the coroutine mechanism, a component can reuse a single kernel thread through multiple coroutines. In this example, a Python server component first receives an incoming request R1 and assigns it a coroutine 1 for processing. Later, upon receiving another incoming request R2, it assigns coroutine 2 to handle it. During processing, these two coroutines may switch between each other until they eventually ensure their respective outgoing requests. From a non-intrusive view, we can't get the mapping relationship between coroutines and kernel threads. Now we can observe the switching between coroutines. Therefore, for given outgoing requests like R3, it may be triggered by either incoming request R1 or R2. It is hard to know which one is right. Therefore, we propose the DeepTrace system to accurately reconstruct request trace in a non-intrusive manner. Our architecture consists of two core components: agents deployed on each host and a server deployed across the microservice cluster. The agents are responsible for span construction and transition-based span correlation, while the server handles final assembly of request trace. Firstly, DeepTrace utilizes eBPF to collect requested non-intrusively. Inspired by DeepFlow, we attach eBPF programs to 10 network-related system calls to gather the new raw data of request. This raw data generated with each system call includes process ID, system call type, circuit file tuple, timestamp, and message content. This raw data serves as input for constructing spans. During the processing stage, DeepTrace groups the raw data based on process ID, circuit file tuple, and C-term code type. Within each group, DeepTrace passes the message content according to the protocol templates to extract requests and response. Currently, DeepTrace supports passing over 20 widely used public protocols. Finally, DeepTrace pairs request and response to construct spans. To enable accurate correlation between parent and child requests, DeepTrace adopts a transaction-based assertion method. We define a transaction category as a logically related set of requests that exhibit semantic coherence of content. There are two types of transaction. The first one is the nested API relationship. For example, in this microservice, a request carrying the login API always triggers an outgoing request carrying Wi-Fi ID API. Therefore, login Wi-Fi ID constitutes one transaction type. Similarly, register ID query forms another distinct transaction type. The core principle of transaction-based request correlation is that requests from different transaction types can't be associated with each other. For instance, in this example, the outgoing request R2 shares the same transaction type as the incoming request R1, so they can be correlated. However, no association should exist between R1 and R4. The second type of transaction is persistent transaction files. It refers to transaction files that appear in both parent and child requests. This maintains contextual information throughout the entire distributed request lifecycle. Typical examples include user IDs, order information, access tokens, and so on. For instance, in this example, usernames like user1 and user2 serve as persistent transaction files. Requests with identical transaction files should be grouped together. To build a transaction-based span assertion method, we first need to infer the transaction types of spans. We need to solve two problems. First, the nested API relationships are determined by the internal application logic within Visible. Because of interdependency between APIs, requests involving nested API typically co-occur. Consequently, APIs with stronger traffic intensity correlation are more likely to have a nested relationship. API traffic intensity refers to the arrival rate of requests containing a specific API endpoint. Therefore, we use the Pearce correlation coefficient of API traffic intensity to evaluate the probability of belonging to the same transaction. Regarding persistent transaction files, the content of incoming and outgoing requests often contains numerous schema files with identical patterns, such as the post content types, these keywords in the HTTP protocol. If we were to rely solely on identical files in the request content to define persistent transaction files, spans from different transactions could be incorrectly merged. To address this issue, we employ the TF-IDF algorithm to assign different weights to different files. Since schema files appear more frequently, the TF-IDF algorithm assigns them a low weight based on their high frequency. This allows persistent transaction files to receive high weights. After obtaining the weight vector for each request content, We use cosine similarity to calculate the probability that any two requests belong to the same transaction type. Finally, for any given incoming span S and outgoing span D, the probability of a parent-child relationship between them can be expressed by the following formula. Here, PH and PD represent the probabilities derived from nested API relationships and persistent transaction files, respectively. Furthermore, since not all parent-child request pairs will contain usable transaction information, we also incorporate the distributions of causality-related metrics to access the parent-child probability. But this aspect is not the main focus of our work. Finally, DeepTrace performs interactive span correlation within each component. We assume that the child span starts later than the parent span and ends earlier than the parent span. Therefore, for each outgoing span, we can filter multiple candidate parent span based on their start times and end time. We then calculate the parent-child probability for each candidate mapping and select the one with the highest probability as the final parent-child relationship. DeepTrace has already been deployed in several enterprise environments in China. Here's a case study where DeepTrace was used to diagnose a client request timeout. To pinpoint the faulty component, the company deployed the DeepTrace server on a specialized host and installed DeepTrace agents on every Kubernetes pods and OpenStack virtual machine. The entire process required no modifications to any application code. So by querying the timeout-related trace, the operators quickly identify the root cause component within 15 minutes. Our testbed results also show that DeepTrace maintains a tracing accuracy of over 95% even under high concurrency at 1,500 RPS in the testbed. Furthermore, it achieves an accuracy of 92% for requests with tail latency. Since DeepTrace relies on request content for correlation, it maintains an accuracy rate of 95% even when random request processing delays occur. In summary, we have proposed a non-intrusive transaction-based distributed tracing framework that maintains over 95% tracing accuracy even in high concurrency environments. The framework has already been deployed in multiple enterprise environments, showing its practical value. We have open source the code and welcome to use it. Thank you for your attention.
Thanks, Yantao. Do we have any questions in the audience? No? Well, I have one. I worked with distributed tracing myself for quite some time. And although you showed the accuracy at the end, one of the challenge that we have with distributed tracing, at least the invasive version, is latency. It adds a little bit of latency, and one way to overcome the situation is using sampling. So sampling, of course, can bring some blind spots, but this is a trade-off. Otherwise, the latency in the requests increase with the amount of microservices that are involved. Do you have any other metrics that you measured apart from accuracy, and how did that compare with the other systems that you had as a comparison?
Oh, okay, let me Let me think a moment.
No worries, take your time. Is latency in a non-invasive distributed tracing framework relevant, like it is in Jaeger, for example?
Do rappers know if whether our framework uses latency?
Yeah, did you measure latency? Is this relevant in the framework that you built?
Yeah, yes. You know, when we perform the request accession, except the transaction information, we also use the latency and the duration metric, like like trace weaver. In our emulations, we also evaluate the latency performance of our framework, like the trace, the rate, the latency of trace reconstruction, and the end-to-end performance latency.
Now, do we have any questions from the audience? There, micro. Ah.
Hi, thanks for the talk. It's an interesting technique to use contents of the requests to try to correlate between the requests. Are there applications where the content is obfuscated in some way where it would be hard to use this approach?
Thank you. It's a good question. The content is not always useful because, like the persistent transaction file is not always used in the request content. So, to solve this problem, we also use causality-related metric to assess the parent-child relationship probability. This is done by trace weaver, and WinPass like this works in past. But this is not my main focus. Thank you.
Any other question? No? I have one out of curiosity. So in microservices, distributed tracing gives you one view for the troubleshooting, but usually you have other data that helps you, for example, metrics that comes from the infrastructure or logs as well. Are you planning to integrate other data to do more root cause analysis and add to your distributed tracing, or is this already a system that is done and?
Thank you. That's a good question. I think trace, metric, and logs also is useful information. In microservice, the discrete nature of microservice so sorry, thank you.
All right, let's thank the speaker and we move to the next talk.